Hello everyone, my name is Ji Xuanzhi. I come from George Mason University. Today I will present our work, Learning to Herd Agents Amongst Obstacles, Training Robust Shepherding Behaviors Using Deep Reinforcement Learning. Let me start by introducing the idea of shepherding. Shepherding is defined as one or more shepherd robots try to get a team of agents from an initial location to a goal region. It has many applications such as animal herding and crowd control. There are two major types of shepherding methods, rule-based method and learning-based methods. Rule-based methods consist of a set of rules as a function of the system status. They are easy to implement and can handle complex environment, but fragile due to the difficulty in defining rules for all possible cases. Learning-based methods use machine learning techniques. They do not need the knowledge about the behavior model. However, these learned models have only been trained and tested in simple black environments. To overcome those limitations, we propose a learning-based method that can herd agents among obstacles. By combining deep Q-learning with probabilistic roadmap, we train a shepherding model using noisy but controlled environmental and behavioral parameters. The figure on the left shows the deep reinforcement learning architecture, and the figure on the right shows the probabilities roadmap. The proposed algorithm works as follows. The input is a sequence of 84 times 84 pixels local frames. The output is one of discrete actions in 8 directions. The reward includes 3 parts: moving reward, violation reward, and goal-reaching reward. We will describe the details of these components in the following slides. Firstly, let's see the input. The figure on the left shows the global view of the workspace. Then we choose the shepherd as the center, create an observation space. The figure on the right is a local view, which is our input. In the local view, we need to represent the different objects. We represent the shape as a bounding circle with the center for the shape center. Shepherding is 3 times 3 pixels, and the obstacles and the boundary are the polygon shapes. We also use different pixel values for representing different objects. For example, shepherd is black and obstacle is green. To represent the goal in the local frame, if there is no obstacles, we put it directly in the local frame. If possible, if there are obstacles, we need to inquiry PRM and find the nearest waypoint as a sub-goal. We put the sub-goal in the local view frame. The figure on the right shows that the yellow point could be the sub-goal. The goals are sometimes outside the shepherd local view, but this information is important for the shepherd. So how to handle that? We connect the shepherd position and the goal position as a line segment and get the intersection of the segment and the boundary of the local view frame. Then we mark the intersection as a sub-goal, which shown in the figure. The output is the discrete actions as illustrated in figure. In every step, one of the 8 directions is selected by the neural network, and a force along that direction with fixed magnitude is applied to the shepherd. In addition, to make the action continuous, we add a clip Gaussian noise to the direction of the force. For reward structure, the first part is moving reward, which contains projection reward and path reward. To ensure that the shape is moving in the desired direction and reach the goal as fast as possible, we introduce the projection reward. Let the current shape position to be A, new position be C, and the goal position be B. See the figure, for example, the vector W should be the projection reward. The reward has the same size as the dot product of the vector U and V. The path reward function calculates the difference of the geodesic distance of 2 states by straight line distance without obstacles or probability roadmap with obstacles. We consider 2 factors of violation reward. Firstly, for multiple shape, we need to consider the cohesion of the group. we penalize the group with a large negative reward if the radius of the bounding circle is large. Secondly, we want the shipper to have effective exploration around the group, so we penalize the shipper with a large negative reward if the shipper is far away from the ship center. Finally, a large positive reward is given when all the ships reach the goal region. To train the shepherding controller, we add random noise to the behavioral and environmental model. For instance, we change the group behavior coefficients randomly. We also consider two types of obstacles in the environment: fixed obstacles and perturbed obstacles, to study the robustness of the trained controller. The group behavior model used in this paper has three forces. Separation force maintains a distance from others. Alignment forces steers the ship with others by velocity, and cohesion force moves the ship towards the average position. In our ship model, we add fear force to maintain a distance between ship and shepherd. The behavior of the ship is a weighted linear combination of these forces, and by changing the weights, we can simulate different group behaviors. We first consider the environment with predefined obstacles. In practice, the environment is usually fixed, and the ship routinely moves toward one location for grazing and the other location for drinking. Therefore, we create a fixed environment as shown in the figure. We set two positions and alternate between these two positions at the start and goal. Figure shows two trajectories in the opposite directions that successfully hit a group of three ships in the filtered environments. Since the challenges faced in hitting the group in these two directions are different, we split the filtered environment into filter 0 on the left figure and filter 1 on the right figure. With this fixed environment, we randomly change the group behavior's parameters during training. Next, we train the controller in environments with randomly perturbed obstacles. Figure shows examples composed of fences which partition the space into long corridors with narrow gaps and shelters. To train the controller, we create three layers obstacle environments, as shown in the figure on the left, and perturb the position and angle of each fence using a Gaussian noise. For the gaps formed to two fences, the shorter fence may appear or disappear randomly, thus change the difficulty of the hitting problem, as shown in the figure on the right. We also randomly select the start and the top, and then the goal from the bottom in the environment and vice versa. Similar to the scenario with fixed obstacles, group behavior coefficient are randomized. To evaluate the proposed method, we highlight the effectiveness and robustness of the trained controller over the route-based approaches. The trained controller is tested with random noise injected to our environmental and behavioral models. There are two route-based models we want to compare. The simple rule method, the shepherd with simple rule moves straight behind the group to a new steering point. The complex rule method, the shepherd uses a stop-turn steering policy, which allows shepherd to stop the ship and steering them toward a new direction. We compare the robustness using two metrics, success rate and path quality. We measure the path quality by completion time and path length. This experiment shows the success rate in different levels of fear force in the fixed environments. From the figure, we see that the proposed model maintains a higher success rate compared to the other methods, even when the controller group becomes more difficult to hurt. This experiment also shows the completion time of the success cases for different levels of fear force in the filtered environments. In this plot, the learned model spend less time herding than the other two route-based methods. In addition, the standard deviation of the completion time is also the smallest among all methods. The plots show that the learned model completed the hidden task as soon as possible, and it's also robust to maintain its quality. Similar, our experiments show that the path lengths obtained using different levels of fear force. For this plot, we find that the learned model most significantly lies compared to that controlled by the road-based methods. We also know that the standard deviation of the mean path length with the learned model is smaller than other rule-based algorithms. This indicates that the learned model is robust to maintain its efficiency even when the group becomes more difficult to handle. To test our controller in the protect obstacles, we train the model in 3 layers, but test it in 4 layers. The group behavior parameters are randomized in the range identical to those used in the training. The figure shows several success rates of the shepherding by the trained model with different number of gaps. The figure shows the success rate of the 4-layer perturbed obstacle with different gaps. Consequently, the success of the learned model remains at least 15% higher than the rule-based methods. The video shows 3 methods for shepherding in 4-layer obstacle with U-turn and gaps. First, the simple rule. We can see that the path quality was not very good, and then finally it's failed. Then we show the complex rule. It's better and the success. The last is the learned model. It's success. We can see the different path comparisons in these 3 figures. We also conduct experiments for robustness of controller learned from perturbed obstacles. We create the 4-layer obstacle environment with 4 gaps. Here, the obstacles are fixed. The figure shows the success rates with very fear force in these environments. When the fear force coefficient is small, the simple rule and the complex rule method share similar success rates, but our method performs better. When the fear force coefficient is larger than 10, the complex rule method outperforms simple rule method because of its more advanced policy. Our controller has a similar result as the complex rule method does. We measure the path quality as before. Figure on the left shows the completion time of successful cases under different levels of fearfulness. The results show again that the learned model spends less time on average than the shepherd with the complex rule method. Figure on the right shows that the shepherd controlled by the learned model moves less than the controlled by the rule-based methods. Here's the conclusion. In this work, we propose the first no learning-based method that can herd agents among obstacles. The experiments show that the trained controller is robust to the uncertain in the group behavior model or in the environment model. In addition, the proposed learning-based method has higher success rate, shorter completion time, and path length than the traditional rule-based method. There are several limitations in this work. The proposed method can only handle a group of 2 to 4 agents and the environments with few path homotopy classes. In addition, different controllers must be trained for different types of environments. Thank you very much. Please visit our webpage for more information. Thanks.